Hi everyone, welcome back. So for this video, we're still on module number 5. So for the first 3 videos, we were able to discuss the bending stress. Okay, so for the succeeding 2 videos, we are going to discuss the shear stress on beams. Okay, like what I've said a while ago, or for the other video, if I have here a beam and I am to apply a downward load, so ito yung beam, I am to apply a downward force, there will be a bending. So the stress above is uh, what you call the normal stress, which is in compression, and the stress below is tension. Okay, those two forces are causing the bending of the beam. Okay, but bending stress is not the only stress present. We also have the shearing stress, okay, or the shear stress if loads are applied. Okay, so for the derivation of the shear stress, for the equations or the working equations that we're going to use for this topic, kindly refer to the video that I have uploaded in our Google Classroom, so we can proceed right away with the solving problems, so as not to delay or ma-stuck tayo sa pag-derive ng equation. Okay? So, we have here a simply supported beam which is loaded by 8 kilonewton per meter, and the shear and moment diagram were already drawn. Now, if you're already on this video and you're still not familiar with drawing your shear and moment diagram, I suggest review some of my discussions on how to draw your shear and moment diagram. Okay, so here we have the shear as 24 and negative 24. So you have here 3 blocks of wood and it was glued on this portion, and it was also glued on this portion. Now, according to the problem, we need to determine on the glued part and the maximum, this should not be bending, it should be shearing stress, the maximum shearing stress on the block. So what is the maximum shearing stress of the block? So we have here our working equation to be shear is equivalent to VQ over I times B. Okay, so the V here is the max or the shear, and Q, it is the area times the lever arm with respect to the location that we are trying to look for the shear. I is the moment of inertia of the cross section, and B is the thickness of the cross section, and that would be this. Okay, so we have shear. So since we are to determine the maximum shear stress at this glued portion, we all know that the maximum shear is positive 24. So we already have our shear there. Okay, now for the Q, we need to solve for the Q, we need to solve for the I. Okay, so Q is equivalent to area times Y bar prime. Okay, so what area are we trying to pertain here? A prime Y. Okay, so take note, I am looking for area above the point of the above the point of the location that we are trying to determine. So take note here, if I am to redraw that. Okay, so we have it here. This here is the neutral axis. Okay, and okay, so we are trying to determine the shear stress here. Okay, so the area that I am going to consider would be the area above. So that would be the area above the location I am trying to determine. It can also be, pwede rin, na the location below. I can also use this. Okay? It will still be the same because I am going to use what you call the lever arm. And that lever arm will be coming from the centroid going to the neutral axis. And this is y bar prime. Okay? So A, therefore, Q therefore is equivalent to what is the area? We have 100 100 mm, and we have here 50 mm. Okay, so the area would be 150 mm, 150 mm times 160 mm times the lever arm. That would be the centroid of this first rectangle is 50 plus 50, therefore that is 100 mm. Okay, and that is equivalent to 2.4 times 10 raised to 6. Okay, no. Take note, the area we're considering is the shaded area lang, and that is 100 by 160. So mali yung 150, it is 100. Okay, so that is 100 times 160, and that is 1.6 times 10 raised to 6 mm raised to the third power times, convert natin into meters. Okay, we have here 100 mm is to 1 meter. Therefore, Q is equivalent to 1.6 times 10 raised to negative 3 meter raised to the third power. Okay? So, meron na tayong V, Q, B, and I. So, we can now substitute. So, tau is equivalent to what is V? We have 24,000 Newton meter times Q, which is 1.6 times 10 raised to negative 3 meter cube, divided by what is I? So I is the moment of inertia of our cross section, and that is the base of 0.16 times the height of 0.3 cube, divided by 12 times B, or the thickness of our cross section area, and that is 0.16. Therefore, tau is equivalent to 666.67 kilo pascals. Okay, that is the maximum shear at the glued portion. Now, the next thing we need to do is the shear max of the cross section. And our working equation would be 3V over 2 times the area. Okay, and that is equivalent to, we have 3 times the maximum shear of 24,000, that is in newtons, divided by 2 times the area of 0.3 times 0.16, and this is in meter squared. Therefore, tau is equivalent to 750 kilo pascals. Okay, what if I am going to use this equation? I'm going to use the equation here. So let's see if they will have the same answer. So other solution, we have here shear max is equivalent to V Q over IB. Okay? So, isolve natin si Q. Now, for the Q, what I'm going to consider here as my Q would be this whole section. Okay? Itong buong section. Because I am now determining the shear max at the neutral axis. Okay? So, shear max, if I am to redraw that, it would look like this. So, the half portion, so that is this. Okay? And the area that I am going to consider would be everything above the neutral axis since I am determining the maximum. Okay? So, maximum will occur at the neutral axis. Okay? So, substituting shear or tau max, no. We still need to solve for the Q. So, Q is equivalent to the area of 0.15 times 0.16 times the lever arm. So, this is 100, this is 50. Take note, that is 50, that is 100. Okay? So, half of 150 is 0.075. Okay? So, Q is equivalent to 1.8 times 10 raised to negative 3 cubic meter. So, we can now substitute on our shear. So, shear max is equivalent to what is V max? That is 24. So, 24,000 newtons divided by or times Q. What is our Q? Q is 1.8 times 10 raised to negative 3 cubic meter divided by what is our moment of inertia? The moment of inertia is 0.16 times 0.3 cube divided by 12 times the B or the thickness of the cross-section area, and that is 0.16. So, tau max or shear max is equivalent to 750 kilopascals. They should have the same answer. Okay. So, we have here problem number 7, and we have here an I-beam or a wide flange. So, W12 by 40, so this is W12 by 40, is used as a beam. If the vertical shear force acting at a certain section of the beam is 16 kips, okay, so shear is 16 kips. Determine the following at that section. Number 1, minimum shear stress. Number 2, maximum shear stress. And on the web shear stress on the web. Okay, then the percentage of the shear force that is carried by the web. So for number 1, we can say that the minimum shear stress will occur at the junction between the wide flange and the web. So dito mangyayari at this point, it is where our minimum shear stress will happen. So we have here our working formula. Part 1, working formula is T is equivalent to VQ over IB. Okay. Now, we need to solve for Q. So how are we going to solve for Q? Q is equivalent to A1 Y1 bar. Okay? Prime. Okay. So ano yung A1 natin? Ito yung A1 natin And yung y natin would be from the centroid going to the neutral axis. So Q is equivalent to what is A1 prime? We have 8.01 times the thickness of 0.515. Now for the lever arm, it would be 0. It would be 11.9 divided by 2. Then isusubtract natin yung 0.515 divided by 2. Okay? Minus 0.515 over 2. Therefore, Q is equivalent to 23.48 inch cube. Okay? So, pwede na nating i-substitute. So, tau is equivalent to what is V? We have 17, and that is kilopound. So, times 10 raised to 3, because kips, ibig sabihin ng kips, sana yung kips? Kilopound per square inch. No. Kilopounds. K-I-P-S. Kilopounds. Okay? So, times 10 raised to 3. Tapos, what is Q? We have here times 23.48 divided by I. So, we have here a wide flange of 12 times 40 or 12 by 40. So, pwede natin kunin yan from the table. And from the table, I is equivalent to 307. Then for the B that we're going to consider, or the thickness, would be the thickness of the web, and that is 0.295. Therefore, shear is equivalent to 4,148.18 psi. That is the minimum. Now, for the maximum, we have here number 2. For the maximum, it will occur at the neutral axis. Okay? So, since it will occur at the neutral axis, I am going to consider all the area above the neutral axis. Okay? So, let's say this is Q1. So, we have Q2 is equivalent to the area Q1. So, Q1 plus, we have the area here that is 11.9 minus 0.515 times 2 divided by 2, that is for the height, times the thickness of 0.295 times the lever arm, which is y2. So, magiging 11.9 minus 0.515 times 2 divided by 4. Kasi kay 2, ito lang. So, divided by another 2. So, that is divided by 4. So, hindi kasi natin sinimplify, kaya humaba yung ating equation. So, Q2 is equivalent to 27.84 inch cube. So, pwede na natin siyang i-substitute. So, this is a shear min. So, this is shear max is equivalent to, what is the value? We have 16 times 10 raised to 3 times, what we have here is, Q rather. Ang Q natin is 27.84 divided by our I. Our I is taken from the table, which is 307 times the thickness. So what is the thickness? The thickness, or the B that we're going to consider here is the same. So ito yon 0.295. Therefore, shear max is equivalent to 4,918.46 psi. So for those of you who are wondering why am I still considering the 0.295 as the thickness or the B, take note that the maximum shear stress would occur here and the thickness is 0.295. Okay, so that is for part 2. Now for part 3 of number 7, so niredraw ko dito yung ating section. Then I drew here the stress diagram. So the minimum stress is at the junction of between your wide flange and your web. So that is here, that's there. Then the stress there is 4,148.18 psi. Then at the neutral axis, we have the shear maximum as 4,918.46 psi. So that is a parabolic curve there. Okay. So to determine the percentage of shear force that is carried by the web, it is simply the area of your web times the area of your shear stress. So the shear of the web is equivalent to the area. So ano yung height nito? That is 11.9 minus the thickness of the flange. So 11.9 minus 0.515 times 2 because we have 2 flange. Yun yung area. Then for the area here, let's consider this as a square or rectangle rather. Then here is a parabola. Okay, so times we have here the area of 4,148 plus ito we have here or time plus, and the area of a parabola, if you can recall from your statics of rigid bodies, it is 2/3. Okay, 2/3 of the height. So ano yung height nito from this point to this point? That is 4,917 minus 4,148. Okay, and the shear on the web is equivalent to erroneous. So the shear on the web that we're trying to solve is erroneous. Why did I say so? Because take note that the thickness of the flange is 0.295 already. So with this is the thickness of the web rather is 0.295, but what I am using is 0.515, and that is the thickness of the wide flange. Okay, so that is erroneous. So I repeat, the shear of the web is equivalent to the wide flange here. Okay, I forgot to multiply here the thickness of the web. So, kulang tayo. So, tama yung 11.9 kasi ibabawas natin yung thickness ng flange, but we need to multiply it by the thickness of the web. So, we have here 11.9 minus 0.515 times 2 because that is the total height minus the thickness of the flange times 2 times, okay, the thickness of the web, and the thickness of the web is 0.295. Okay, so times the area now of the of our shear stress, and that is 4148.18 4148.18 plus Take note that for a parabola, the area of a parabola is 2/3. Okay, 2/3 times 4, 9, 1, 8. So what we were able to compute is 4918.46 minus the value of 4148.18. 4148.18. Therefore, the shear of the web is 14,948.44 pounds, and that is the shear on the web. Okay, now to determine the percentage, the shear on the web divided by the shear is equivalent to 14,948.44 divided by the total shear, which is 16,000. Yes, so that is 16,000 is times 100%, and that is equivalent to 93.43%. Okay, which means that 93.43% of the shear is being carried by the web member, and the remaining is being carried by the wide flange. Okay.